Today we're going to be learning computational redstone from someone who knows about that sort of thing. I guess I probably should introduce who you are.
That sounds like a good idea.
I should probably ask you, who are you? As you can probably tell, I am not used to making these sorts of videos.
So I am Mattbatwings. I am a redstone / computer science YouTuber.
In short, he's a very smart cookie. Me and Matt spoke for 5 hours. We took a look at a bunch of his previous projects, he explained some computational redstone concepts, and I even had a go at some myself. He has ranked his projects from easiest through to hardest, and we're starting things off on level 1 with Flappy Bird.
It was the first kind of big-ish computational build I ever made.
Do I start the game? I'm kind of nervous.
Yeah, go ahead and press that button.
I'm more nervous for my own skills at Flappy Bird. Oh, I forget that Wait, did I die?
Did you die on the first pipe?
I died on the first pipe. Right, here we go. I feel like I can do well here.
You got this.
Oh, asking me to showcase how your games function is never going to end well. This is how it is supposed to look. Well, the redstone contraption itself is incredibly impressive. My skills at using it are not impressive. What I'm kind of most impressed by here is it's not that complicated. Like, it's complicated, don't get me wrong, but like it's not that big.
Yeah, no, the form factor is really, really nice on this one.
You could feasibly have this on like a survival multiplayer server.
Definitely, yeah.
After my embarrassing defeat at a Flappy Bird, I wanted to try and redeem myself by guessing how this machine works. So my guess is that every single time you hit the tripwire, it increases your signal strength by a certain amount, and then obviously that gradually decays. So then if you jump up a few times, it will add onto itself.
Yep, that is exactly right.
Okay, well that's very...
Literally.
Okay, that makes me a little bit happy.
All this button does is it takes the current signal strength, adds 3 to it, and puts it back in.
Kind of glad that on level 1, the first one, we're not quite lost yet. This would be a tricky video to record if I was immediately completely lost.
Next is the pipes. So I needed to figure out how to generate a pipe in a clean way. This first part here with the target blocks is just another red coder. So if you put in, I don't know, some signal strength, you can see that only one torch is on.
Yep.
Wherever that torch is, this next part of the circuit just makes it so that it puts a signal strength of, I think, 7 onto this tower.
Very smart.
And what that does is it cancels out a 7 long gap here.
That's very smart, and that makes total sense.
From there, the random pipes are sent across the screen using repeaters and observers.
Yep, nice and easy.
And what's funny is that if you notice on the very front of the screen, the bird is in the first column.
Yes,
so,
okay.
You see where I'm going with this?
Yeah.
You can use this edge here to do an AND gate between the bird and the last column of pipes.
That's so smart. So if the bird was in the middle of the screen, or even just like 2 blocks further over, probably would have been
10 times harder.
10 times harder, right? Like it's way more complicated. But because it's on the edge, you have that side to be able to just compare them and be like, yep, cool. At this point, things were going well. I was familiar with all of these concepts. All of these were circuits that I recognized. So let's move on to build number 2. Is it Connect 4?
Yes, it is.
Okay, so it's a digital Connect 4. Okay. After my embarrassing defeat of Flappy Bird, I was feeling the pressure. But after an incredibly long game... Wait! Yes! Yes! I think I won!
Oh, wait. Did I lose?
Yes!
Did I lose? No!
Yes! Yeah. Oh, my goodness. Oh. Wow,
oh my goodness, good game.
Well, you may have built the redstone contraption, but who's the real smart one, eh? It's definitely still Matt. So let's take a look at how this thing works.
You only have to think about 1 column at a time. Probably the hardest part of any game like this is gravity. So it basically uses a spiral, or I guess a downward torch tower. And the first thing it does, it sets every latch from top to bottom. But obviously, as you know, if you just only did that, then it would look like this, right? It would just set them all, and it would look like that. But then it does a second thing, which is if a latch becomes set, it resets the latch above it.
Right, okay.
So if you think about it, we set this first one, and then we set the second one. It became set, so it's going to reset the one above it.
Right, okay.
And it kind of follows this pattern. And then by the time you get down to here, it's going to set this one. That became set, which resets this. And it is also going to set this one, but it didn't become set. It was already set. So it doesn't reset the one above it.
Interesting.
The next question is, how do you switch between X's and O's? And also, how do you make it remember that it's X's and O's?
Yeah, that's the big question for me, because I have zero concept for how that would go.
Let's start with the orange part. So the orange part, there's 2 inputs to it, and it's very simple. If the top is activated, it shows the O.
Yep.
And if the bottom is activated, it shows the X.
Perfect.
And then there's a repeater lock here. So you can put a 1 or 0 into it, and you can also lock it, obviously. And now what's interesting about this is when the repeater is unlocked, the display is canceled. But when it's locked, it will not only display the thing, but if it's locked with a 0, it'll show an O. And if it's locked with a 1, it'll show an X.
Right, okay.
So if I turn on this power and lock it, it shows an X now.
Okay, that is interesting. And
if it's unlocked, then it doesn't matter what I put in here. It's just going to show nothing because the cell is not occupied yet.
Okay, interesting.
I took the gravity SR thing in the blue.
Yep.
And I put it behind a bunch of these displays all stacked on top of each other.
Yep.
So when you drop a chip, wherever the chip lands, it's going to lock that repeater.
Makes sense. Okay.
Then I connected all of the green inputs together, the signals that control whether it's X or O. I combined them all together into one line.
Yep.
So right now they're all off. And if we press this note block, then it's going to go down and lock that bottom repeater, which locks it with a 0. Because again, they're all connected and it's set to 0. So if we set it to 1 now, this doesn't change because it's still locked. But if we drop again...
Makes sense. That makes sense. You're trying to send an X to all of these modules, but they will only display the X when they're being powered by the cascade thing. And then the locking repeater is important because obviously when it changes states, that is then acting as the memory storage for what it was. Yeah. Like what it has been historically. Interesting. So at this point, I was still in the realm of understanding, but barely. Let's move on to build number 3. This seems like a big jump. I just want to throw that out there. Like,
okay, in my defense, I don't have many builds in between these two. I was looking at my builds and I was like, shoot, do I have any in this like medium size? I really don't.
I think we might have left the realm of understanding. This is a functional paint program in Minecraft. This does require a resource pack. Matt has retextured the 16 different power levels of redstone dots to be 16 different colors. Because redstone dots aren't used that often inside of redstone contraptions, it makes them perfect for retexturing and perfect for creating displays like this one.
Up here is where you can select what tool you want, what thickness you want, and what color you want.
My goodness. So the first thing that I wanted to do was fill in my canvas. Well, that's satisfying.
It's so satisfying.
That might just be one of the most satisfying things. And from there, I went on to create potentially the most horrific piece of artwork ever. It was meant to be a love heart with a smiley face on the inside. I don't know. I don't think you realize like how much you didn't have to go as above and beyond as you have done. Do you get what I mean? Because it's like most people would have been pretty satisfied with like the paintbrush and one thickness and then the colors. What motivated you to just keep going?
It kind of was just like, oh, these things would be nice to have. And then the list kind of grows as you work on the project.
Yeah. Now, obviously, at this point, the builds are so big, it's impossible to explain the entire thing. So I asked Matt for a few features that he could quickly explain.
Okay, the thickness changer was an idea from the beginning. We had an idea for a circuit that could use different signal strengths to naturally like spread out the signal more.
Is that almost like the Flappy Bird style pipe thing, or am I completely off the mark?
Yes.
Like maybe the fill tool, it would be interesting to know how that works.
Let's say you want to change his mouth to blue.
Yep.
So it's what's called a recursive algorithm. It kind of calls on itself to continually do the same thing and spread out in a way. So we're going to start by placing a blue here.
Yep.
That's a given, no matter what the color is.
Yep.
But then it gets the current color in mind, and it looks at the 4 surrounding cells.
Yep.
And it tries to see if any of them are also red. If any of those 4 surrounding cells are red, it's going to do the exact same thing. It's going to set it to blue and check around those 4 neighbors to see if any of those are red.
Right.
So in this case, it would see that only this one is red, and we're going to repeat the process. Now we're going to check this neighbor, this neighbor. We're going to see that this one's red.
Yep.
So set it to blue. And yeah, you can see how this repeats and naturally goes out and fills anything that is red and connected to it.
So I have a few questions here. So number one, the red color is based purely on signal strength from that dot, right?
Yeah.
It knows the signal strength of the original pixel that it tried to fill. And then I guess is it then comparing signal strengths? Like, is it then like looking for that signal strength around it in redstone terms as opposed to color terms?
We call them signal strength comparators. So they will be able to tell whether the signal strengths are equal or not. So the first thing you do when you actually press the bucket tool is it puts whatever color is on the tool currently into some kind of memory.
Yeah, okay.
And then it uses that memory to compare to the neighbors as it does this recursive algorithm.
We've got a recursive algorithm of questions because every single time you give an answer, I then have like four more questions that come up. Like, I understand that theoretically. In terms of redstone,
you see how there's kind of one main redstone line here on every cell? When that gets activated, that means that the cell is being painted by the bucket tool. You'll also notice that there are 4 signals going to each of the 4 neighbors that are coming out from this main line. These are all attempting to spread to the 4 neighbors, and the only ones that are actually going to be allowed through are the ones that have the comparator unlocked. And that comparator is only unlocked if that signal strength that got saved from the beginning is the same.
That does make sense. Yeah. I never would have thought of it. I never would have been able to design anything, but that totally makes sense when you say it like that. Now, at this point, I thought things couldn't get any crazier, and then Matt took it about 3,000 levels higher, and that will be coming towards the end of this video. Before we get there, though, we're going to dial things back a little bit to my level. When I was speaking to Matt about the format for this video, he suggested that in the middle, we should have a little school for computational redstone where I would learn some lessons and then be given a project to complete, as he observes. Oh my goodness, I can't do anything with anyone watching me, let alone someone as smart as Matt. So I tried my best. Let the lessons begin.
Probably the first thing that a beginner should learn about is logic gates. Here, this is the not gate truth table. The column that says A is the input, and the column that says not A is the output.
Yep.
So what this means when you read this is if you put in a 0, or if the lamp is off, the output is 1, or the output is on. And the other way goes as well. If the input is 1, the output is 0.
Yep.
And so the easiest way to make that in Minecraft is a redstone torch. Mojang was nice enough to basically give us a NOT gate in 1 block.
Yep.
So not much to describe there. Then we have the OR gate, which follows a slightly bigger truth table because there are 2 inputs this time, A and B. And because there are 2 inputs, you have 4 different combinations. And the way the OR gate works is kind of how it's read. It's on if A or B are on.
Obviously, they're used all the time inside of redstone contraptions. A lot of the time, like a lot of this vocabulary probably doesn't get directly used. You just kind of end up with them in redstone contraptions. AND gates, they're more a specific logic gate. Like I'm normally pretty aware of when I've got an AND gate inside my build.
Yeah, AND gates are usually pretty purposeful, just like the name says. It's only on when A and B are on. You can see from the truth table.
I'm feeling good about this lesson so far. However, yeah, the old exclusive or maybe... Like, I understand obviously how they work. I cannot remember the last time I built one.
They're not really used in non-computational, but XOR gates are really nice. They give an output when you only have 1. If it's 0 and 1, that's an output. Or if it's 1 and 0, that's an output.
Yep.
But if it's 1 and 1, that is not an output. You can only have 1 at a time. To give people an idea of why logic gates are useful, as it turns out, they're kind of useful for everything. So not only do they make things like calculators and computers possible, they're really useful for small circuits with like games and stuff as well. So in this example, we have rock, paper, scissors.
Perfect.
This first circuit is to detect whenever there's a tie.
Yep, that makes sense.
All I have is an AND gate on every matching pair here.
That makes a lot of sense.
The other thing you can do is obviously a wind detection.
Yeah, this one I guess is a little bit more complicated, right? So I guess you've got AND gates, but they're linked between the things that would beat one another. If that makes any sense.
I tried saying that sentence earlier in a small way. There's no way to do it.
There's no way to say it in a way
that's a long sentence
that makes sense.
If you have these 2 circuits already built, how would you detect for the right side winning.
You're detecting tie, and then you're detecting the left side winning. So then any other option means the right side has won.
Yeah, exactly.
Thank goodness for that.
One of the first builds that people try to make with logic gates is an adder. This is why logic gates are powerful, because even with just a few of them, you can start doing things like adding binary numbers together.
There's XORs, there's AND gates. I can recognize all of the gates.
Yeah.
I'm not entirely sure why they are sequenced in the way that they are.
The basic idea is to count how many ones you have in each column. Based on that, you either need to like give an output, or maybe you need to carry over, or maybe you need to give an output and carry over.
Right, okay.
So these logic gates are to figure out which case you're in. 1 plus 1. So we get a trigger on this AND gate here, which is telling it to carry over to the next place, and it ends up going all the way out to the output. So the output is saying 0, 1, 0, and in binary that is 2.
Okay. That is the okay of a man who is starting to struggle to comprehend things. Maybe we take a look at encoders and decoders.
So this first circuit, it's just a combination lock.
This is like the old school lever combo lock, right?
So one of the basic components that get used all the time in Comp Redstone is called the decoder. All a decoder is it's just a bunch of combination locks for every possible combination of the bits.
Right, okay. Okay.
So right now it's 0, 0, 0, and we have a combination lock for that.
Oh,
if I put in 0, 0, 1, we get this one. No matter what combination I put in, there's a line to detect it. And that's why it's called a decoder, because it takes a 3-bit signal and it decodes which signal you're talking about here.
So this has never made more sense to me.
One example of what decoders are used for is screens, because with 2 decoders, you can detect for an X coordinate and a Y coordinate.
Yep, makes a lot of sense.
So here we have 2 3-bit numbers, one for X, one for Y. And so right now it's 0, 0, and that's why it's kind of in this bottom left corner.
Yep.
But if I, let's say make the Y coordinate 4, it'll jump up to the coordinate 0, 4. We're going to do, this is called an encoder. So it's kind of like a reverse combination lock.
Yep.
There's only one input, and it's just, when you turn it on, it shows you what the combination is.
Yep, that makes sense.
So you can customize what you want to show here. If you want it to show 0, 1, 1, you just put the repeaters here. You can encode it however you want. Stacking this out, you can have a bunch of different lines to encode all the different binary numbers.
I'm assuming this is like a binary encoder and then a binary decoder.
Yep, that's exactly right. So we can now send 7 signals over just 3 wires.
I mean, I can immediately see how that would be incredibly useful. This is so you called it an SR latch, and I'm going to stick with that. Yep. I'm going to stick with that for this, because I'm now a computational redstoner.
Comment below whether you're in the SR gang or the RS gang. We're going to start a civil war. In computer science language, this would be a data latch.
Right,
but it's just a repeater lock.
And then this one over here, it's just a little T flip-flop, right?
Pistonless T flip-flop.
I was going to say,
because for some reason, people in Comp Redstone have a vendetta against pistons.
That's fair enough.
I say people like it's not also me. It's also me. I hate pistons. So this thing is a serial transmitter. So you can put in a code here, press this button, and it'll get sent to the other side with just 1 wire.
Let's say, would this be number 5?
Whatever you want.
Okay. What? Okay, now this has lost me a bit. I'm trying to. Oh no, this makes a. Wait, yeah. So we're using 2 tick pulses, and then of course that makes sense. And then as this comes in, this is an SR latch, which then unlocks all the repeaters until it turns off. And then it flicks back off, and then you've just basically stored... Yeah, okay. You've like stored where the redstone bits were powered from this line. That makes a lot of sense. That looked like witchcraft when I first did it.
That's what's so cool about this. Whenever I show people, and maybe they're not paying attention, or maybe they're just... It's like, wait, what just happened? What? The pattern just teleported.
Yeah. That took me a minute.
So I want you to put whatever image you want here, and then press that button when you're done.
Oh, okay. So this is almost like what we had there. Wow. Oh, I love that. I absolutely love that. So this is the same circuit. This is a similar circuit, but it's just laid out in a slightly different way. That's outrageously cool. Like, I can actually see use cases for this myself. So after that absolute speedy rundown, it is now time for the part I have been dreading. Matt has provided me with a handful of components and has asked me to create tic-tac-toe. Prepare yourselves for an absolute fumble fest. What I'll do is I'll run you through what our idea is, and you can tell me whether or not this is really silly.
That sounds perfect.
I'm going to clone each one of these modules 9 times over. So I'll have a 3x3 grid. I'm going to have to hook up a redstone circuit that detects when any of these buttons have been pressed, and that's going to trigger my T flip-flop, which will toggle between the naught and the cross. And then all I have to do is connect up each one of these buttons to the corresponding units, I think.
That sounds good to me.
Cool. Okay, and I don't need any wind detection or anything like that. That would be complicated. Okay, I've got my 3x3 grid. This is good. So I probably want like SR latches there and then a full reset circuit.
Yep. So you realized you need memory for each cell. Some way to remember that there was a placement there.
Okay, so all of these need to be connected to the T flip-flop circuit. So that's all now connected up. Okay, cool. So then I need to detect when any of these buttons are pressed. Probably the best way to do that is, again, I would probably use observers personally. So then I need to fit an RS NOR latch in this gap here. That is possible with droppers. It just feels like it's not the redstone computer way.
It's totally up to you.
Should I do it the way that I would do it, and then we can see what computational redstone looks like from my perspective? Yeah, so that's like my super, again, very Minecrafty redstone way of doing. It
is very nice. It's very small. Look at the middle row.
Oh no!
How did that even happen? What?
What? What? No.
I think you should keep it. It adds character.
No, I can't keep it like this. It's monstrous. That's because I was doing it and I was like, why do the bottom two match up height wise, but then I keep having to do weird stuff for this top one, and I was like, that's so strange. They keep getting out of sync. Okay.
Yeah, what is that math? That shouldn't work. No, you gotta keep it.
I told you, I'm under pressure. All right, fine, it can stay. But I want it known that I don't want it to stay. This is entirely your fault that this is staying this way.
Okay, in an effort to save time, I'm going to tell you that this is the incorrect wire to wire. I'm gonna let you figure out why it's wrong.
No, it is very wrong. Yeah, for goodness sake. That's actually kind of annoying because then you have to flip them over one another.
Yeah, you have to flip the left and right. The middle is fine to go to the middle, but the left and right need to swap. Where are you planning to have the observers?
This is the thing that I probably should be working out at this point in time. Do you know what I would probably do? Something like this.
Ooh. Wait, does that just work? Then the torch activates the note block?
It should do. Have I made myself look stupid? No.
Yeah, that works.
That works. It'll fire twice, but...
Okay, that's really nice, actually.
Cool. I will reset it, and I'm going to test the bottom row. That seems like the way to do things. This is a promising...
Nice.
This is a promising situation here.
Oh, look at how these O's look.
Oh no! Again, I just want it known. I want it known. I wanted to change this, alright? After a few initial problems of cross wires and things not being connected properly, this thing was now functional. I'll go in the middle.
Alright, full game.
Full game. This is all going to be functional now. Everything's looking good. Everything's looking good.
Let's go!
There we go. We tied.
Oh, I love it.
That's the best way to be, but that functioned perfectly, flawlessly first time, which is crazy.
Okay, now I see why you want it on your channel. The edits.
This was genuinely, when you suggested this, I must admit, I was flustered. And you might have been able to tell I was flustered because I couldn't really see how I was going to be able to do it. And I think for about the first 20 minutes, I was slightly panicking.
No, but you literally sat that you worked through every single problem in a really nice manner. Great job. This was really good.
And just as I was starting to entertain the idea of taking on larger, more exciting computational redstone projects, We went into Matt's next world, and I will show you that in 1 second. But before we do, I think it's worth mentioning, Matt has a YouTube channel, Mattbatwings, and if you're into this computational redstone stuff and you want to see even more crazy builds, then it will be down in the description. Please do check it out. What? Like, okay. Okay, go ahead. You know what? You can do the talking on this one, because I don't even think there's any point in me saying anything at this point in time. Go ahead.
So this is a QR code generator. So there's a keyboard down here, right, and you can basically type in whatever you want. When you press the button over here, it will literally generate a QR code, and then you can actually pull out your phone and scan it, and it will have that data in it. So, for example, if you type in a link, like youtube.com or whatever, and then you generate the QR code and scan it with your phone, it'll take you to youtube.com.
What? I'm editing this video currently, and I am still absolutely flabbergasted.
Boom.
Okay, it has been sent. Like, it kind of looks like it's figuring things out, and I know that's probably not the case.
I mean, it definitely looks like that. Do you remember that serial display I showed you, where you can send one to the other?
Okay. Oh, so this is just a big one of those. Big one of those.
It is, yeah.
How's this looking?
It's good. We're going to have to wait for the second half. It's looking pretty good. This looks good.
Okay, I'm going to get my phone camera out. Let's see. There's no way. If we covered some of this QR code, you would still be able to get to it.
Yeah, let's get the TNT out.
The tick rate is so high.
That scared me for a second.
That made me jump. Yeah. It still works! I'm sure there's a few people down in the comment section who aren't going to believe what is happening here. So please, if you're watching this on a computer, grab your phone, scan that QR code, and it will take you to youtube.com. But here's the crazy part. Matt wasn't even finished. He has 2 more builds that he wants to show me. Shall we have a game? I mean, I'm literally the worst Tetris player on the planet. Probably worse at Tetris than I am at Flappy Bird, and that was pretty painful.
Oh gosh.
Okay,
let's do it.
So I just stand in this gap here, hit the start game button, and then I can push myself onto the pressure plate to move the item over and jump through the tripwire to rotate it. But obviously this is a square, so you can't really see that. I kind of want to like put this one on top of the other one, even though that is a terrible placement. I'm aware of that.
Fair enough.
I just want to see like how these game mechanics work. How did you do it?
Logic. Dedicating 5 years of your life to just play Minecraft instead of getting a real job.
So you got the randomizer that generates the blocks. Fine. You've got things falling through a display that are landing on things again.
I'm decoding for where the piece should be, and then I'm decreasing the Y coordinate to make it fall.
Okay, so it's almost like what you spoke about earlier on, where you have the X and the Y coordinates, and you're gradually decreasing that Y value, and then you've got the rotation of the pieces.
This here is a big memory to store all the different rotation states, and it's color coded by how many you need for each piece.
Yep. Okay.
You can see the yellow is the square here, and there's only one of them.
That makes sense. Yep.
I think the blue is the line, so there's 2. You get the idea.
Oh yeah, of course. Yeah.
And then if you go down a little bit, there are basically what I like to call rotator circuits. They're just a line of repeaters that then feed back into themselves. And so these allow you to switch between different lines of memory.
Okay, so it's like a little counter.
Yeah,
in a way.
It's like a little rotating counter.
Yeah. Okay. What I like about these big complicated builds is they're made up of many smaller, less complicated builds. And although I'll never be able to build something like this, I'm really enjoying the insight. This is good. Okay, this is incredible. But oh my goodness, this expands a long way.
Yeah, this one is this is a big boy.
Yeah. Like I thought it was just all the stuff behind the display. This is stupid at this point.
This is a city.
Yeah. Like genuinely, how, out of curiosity, you know, like how much time is spent on something like this? I mean, you might not want to answer, and that is totally fine.
Well, if I remember right, this one took a month.
Wow. Now I'm going to spare you the pain of watching me be absolutely terrible at Pac-Man for a considerable length of time, but this game functions like Pac-Man. That's the only way that I can describe it. It doesn't feel like Pac-Man in Minecraft. It just feels like Pac-Man. And that is because Matt went through a ridiculous amount of effort to make it as authentic as possible.
The ghosts only think about one step into the future. Each ghost has a target tile, which is just a tile somewhere that it's trying to get to. It looks at the 4 steps it could possibly take around itself. It does some math to think, okay, which one gets me closest to the target tile?
Yep.
And it just picks that one. The way that they're unique is that they have different target tiles. So for example, the red one, his target tile is always just Pac-Man himself.
Yeah, okay.
So it's
that's
like
the lethal one.
very straightforward.
Yeah.
The pink one, their target tile is 4 tiles in front of Pac-Man.
Right. This is the thing about everything that you've said so far today is like all of it does make sense. But then actually implementing that, even programming it is kind of is complicated. But then programming it using redstone wires is like so ridiculously silly.
It's amazing. I love it.
And you know what? I think I agree. It is amazing, and I love it as well. I cannot thank Matt enough for sharing this world with me. Computational Redstone is a side of Redstone that I never touched. I was always way too daunted. He made it all seem incredibly approachable and did a great job at compiling everything together. So thank you, thank you, thank you. And I cannot wait to use some of this in my own redstone contraptions. I hope you enjoyed, and I'll catch you in the next one. See ya!